And so my first thought at the time was, this is just what I've been waiting for, this really cool NASA interplanetary mission. Paid for school, right? And a good topic for a PhD thesis. The second thought I had was, why couldn't this spacecraft be going to Mars? Right? Mars is where all the action is, that's where water is, and of course I didn't know much about Mercury at the time. So the more I learned about Mercury, the more I realized how interesting it is, and now of course I wouldn't change it. Okay, so here are the list of some of the unique properties of Mercury. Why do we care? It's the closest planet to the Sun, and as such, it has the shortest orbital period of 88 days to go around the Sun. Since the demotion of Pluto, it's the smallest planet in the solar system. Significantly, it has the highest uncompressed density of any planet. Some orbital parameters. It has the greatest eccentricity. It's the range of orbital distances from the Sun. The greatest inclination, the tilt of the orbit plane. It has the largest temperature range of any planet. And even though it's the closest planet to the Sun, it's not the one with the highest surface temperature. That actually goes to Venus due to the greenhouse effect. It has a unique spin-orbit coupling such that it rotates on its axis exactly 3 times for every 2 orbits around the Sun. It has a unique magnetic field, weaker than that of the Earth, but similar in other ways, in contrast to planet Venus and Mars, which do not have global magnetic fields. And it is the least explored planet. I looked on a NASA website the other day, and I counted there were 71 either attempted or successful missions to the moon. There were 40.
Can you talk louder, please?
I'll give it a shot. There were 40 attempted or successful missions to Mars, and there's been 1 mission to Mercury. Messenger will be the second. So just to put Mercury in context with some of the other bodies in the solar system, they're at the bottom of the inner 4 planets, the terrestrial planets. So there's Mercury on the left, and the number at the bottom, that's the diameter in kilometers. You see it's quite a bit smaller than Venus or the Earth. And then at the top is how it compares to some other bodies in the solar system, some of the moons. So the top left there is Ganymede, the moon of Jupiter, and Titan, one of the moons of Saturn, both larger than Mercury. Followed by Callisto and Io, 2 more moons of Jupiter, and then here's the Earth's moon. So a little more context. This is a mosaic image of Mercury from the Mariner 10 mission back in the 1970s. And on the right is a telescopic image of the moon from the Earth. And this is just to set up some material for later, but as you can see, they look very similar in many ways. Both are covered in these and lots of craters. So Mercury is actually a pretty difficult object to observe from the surface of the Earth. So here we are on the Earth, and anything we look at, of course, we need to look through the atmosphere. The best you could hope for is to look at something straight up. Mercury being so close to the Sun, it never gets away from the Sun more than 28 degrees. So if you want to observe Mercury at night, right, you want to put the Sun below the horizon down here. So that puts a maximum angle of Mercury above the horizon of close to 30 degrees. So when you're looking at something 30 degrees above the horizon, you're looking through a path length of the atmosphere about twice as much as if you were looking straight up. Of course, that's the best you could hope for. It's more usually lower than that. And at 20 degrees, you're looking through 3 times the atmosphere as if you're looking straight up. You can help out the situation, of course, by going up in altitude. Say you go to one of the telescopes in Hawaii, Mauna Kea, that's at 14,000 feet, but it's still very problematic. You can, by the way, you can also look at Mercury during the daytime, and people do try that, and but you trade off some of the challenges here for other challenges. Of course, during the day, the the sky is bright, right? So there's a large background you need to subtract from your data. The atmosphere is also more turbulent. So this, of course, doesn't stop people from trying. So here's a list of some of the more important observations of Mercury in what I consider to be modern time. So way back in 1865, Zollner observed that Mercury exhibits optical characteristics similar to those of the Moon. Next up, Mueller, 1893, and here's actual words. The curves of the light of Mercury and the Moon agree surprisingly well, and he assigns to the surface of Mercury a nature quite similar to that of the Moon. 1929, based on polarization measurements, Leo found that it is therefore very probable that the ground of Mercury has the same constitution as that of the Moon. Then in the Apollo era, we have Ford and Adams in 1972, and they say the close similarity of the features in the reflection spectra of Mercury and the Moon strongly suggests a similarity in the mineralogy and composition of the soils. So you can see there's a pattern here. Mercury looks a lot like the Moon. And that is going to keep coming up. One of the most distinguishing features of the planet is its high density. And from that fact, we infer that the core of Mercury is relatively large compared to the size of the planet. So here's a cutaway of the Earth, and it's not projecting all that well, but so the Earth has a solid inner core surrounded by a molten outer core, followed by the mantle. So those core regions are made of iron and nickel. So a large fraction of the interior of planet Mercury is iron. So then along comes Mariner 10. So that's the first NASA mission to planet Mercury. It performed 3 flybys. It did not go into orbit. 3 flybys in 1974, 1975. The cameras on board, they imaged just less than half the planet. And so here's some text from one of the first reports. The surface morphology and optical properties of Mercury resemble those of the Moon. In a remarkable detail and record a very similar sequence of events. Chemical and mineralogical similarity of the outer layers of Mercury and the Moon are implied. Here's one of the more important results from Mariner 10. This geologic feature here, it's called a Lobate scarp, and it's actually a thrust fault. And so what they inferred this to result from is as the core of the planet was cooling, it actually contracted and shrank in size. So you can imagine that if you have this solid crust, and then the planet underneath it shrinks, and that creates a compressive force in the surface. And that force has to go somewhere, and then the crust slips and creates these faults. So there's a little diagram of what they think is going on in this image here. And so from that data, they inferred that the planet actually shrank by 1 to 2 kilometers. All these features are fairly young. So you can see this impact crater here, and you see this thrust fault cuts across it. So that means that the fault itself postdates the emplacement of that crater. Some of the other important results from Mariner 10, the detection of a global magnetic field. It's on the order of 100 times weaker than that of the Earth. And this is important because it's potentially evidence for part of the outer core being still liquid and molten. This was rather surprising given the small size of the planet. It had been predicted that Mercury should have lost its heat a long time ago and frozen solid. And this apparently telling us that there's still quite warm in there, it's still liquid. Another finding was that there were widespread smooth plains on the Moon as well. So back in this picture, you can see some of these smooth areas impact craters. They fill large basins. Well, it was tough to tell if those were actually caused by volcanism or impact melting. So when you have these objects and asteroids that collide with the surface, they heat and melt the surface and can cause flows of material that look a lot like volcanic flows. And you see both of those effects on the moon. And so there was a debate from the Mirror 10 images which one is causing a lot of those geologic features. Also, there was the detection of a couple of atoms in the atmosphere of Mercury, hydrogen, helium, and oxygen. And I'll refer to it as an atmosphere, but technically it is not. It's something called a surface-bounded exosphere. Instead of saying that, I'm going to say atmosphere. The point is that density is very low, and it's more likely that any constituent of the atmosphere is going to hit the surface rather than each other. There have been several observations of Mercury since Mirror 10. There have been some radar measurements at the surface. And what's interesting about that is that there have been regions near the poles of Mercury that are bright in these radar images. And those bright areas, this is one of the pictures from that, those bright areas turn out to be associated with permanently shadowed craters. So Mercury is tilted such that there are these regions, these craters at the poles, where the bottoms of the craters never see sunlight. So they're very cold places. And these radar signatures look a lot like those that you get from ice, known ices in other parts of the solar system, like the polar caps of southern polar cap of Mars. So what they think is going on is that perhaps Mercury has been impacted by comets over time. Comets form in the outer solar system and come in toward the inner solar system, hit the surface, carrying water with them. Eventually that water migrates toward these polar regions, and once they go into these cold floors of these craters, they stick and they stay there. They stay there almost indefinitely. A couple more telescopic observations, more atoms in the atmosphere, sodium, calcium, and potassium. And just recently, a few years ago, there were some radar measurements of the surface of Mercury from the Earth that showed that the solid core and the solid crust are actually decoupled from each other. And that's additional evidence that there's a partially molten liquid layer between the two.
Coupled, or are they rotating at different rates or some such?
Yes. So this is one of the more puzzling things that has happened since Mirror 10. Where is the iron in the surface of the planet? So we call it the iron planet since most of the material is made of iron in the core, but it is seen that the surface was actually somewhat devoid of iron. So some evidence for that, there were large impact basins on Mercury. They look a lot like the near side of the moon, these big impact basins. Very similar morphology, but they weren't dark like they are on the moon. And the color was different. So they didn't appear to be composed of the same things you'd expect when you look at the near side of the moon. Also, some of the surface reflectance spectra, it didn't show clear evidence for the presence of iron, at least iron and silicate minerals that you see that's very common on the moon. Of course, a lot of that data suffered from difficulties due to observing through the Earth's atmosphere. There were some other measurements and further analysis of those telescopic measurements that suggested that the composition was low in iron, also in titanium. And a lot of this kind of work is trying to chase the presence of iron and titanium, to tell a lot about the history of the planet and the types of rocks that are there. And so the idea was coming along that the surface of Mercury looks a lot like the bright iron-poor regions of the moon called the lunar islands. And then on comes Messenger into the scene. So in the mid-1990s, this set of science questions were derived based on the state of knowledge at the time. So first, why is Mercury so dense? Second, what's the geologic history of Mercury? What's the nature of the magnetic field? What's the structure and state of the core? And what are those poles what are the materials of the poles? Is it really water ice or something else? And what volatiles are important? That is, what are the constituents of the atmosphere? So you can turn those very high-level science questions into a list of objectives that are a little more focused. You like to image the entire surface in color. You want to measure the magnetic field over time. Look for ice if you can on the surface, or any constituents of the atmosphere that might be associated with them. You'd like to map the composition of the surface in terms of its elemental abundance and mineralogy. You'd like to measure the topography of the surface, detect any irregularity in rotation that will tell you something about the state of the core, and of course you'd like to measure the composition and the distribution of the atoms in the atmosphere. So here's, on the left there's an early rendering of the Messenger spacecraft, and there on the right is the spacecraft itself during one of its tests. I think it's one of the vibration tests. So a mission to Mercury is challenging in its own ways because we're so close to the sun. The sun can appear up to 10 times brighter than it is here at the Earth. So the way this was handled is that there's this sunshade, and all the instruments which are located down here, and everything else sits behind that sunshade. It's essentially just an umbrella there to keep the sun off you. And if you can keep behind the sunshade, then you can actually maintain room temperature. Of course, you can see the sunshade does not go all the way around, and that enforces some very strict pointing requirements for the spacecraft. There's a little launch video. Now, there are much better launch videos you can find on the internet, but this one I think is a little more meaningful because I took it. And so my wife and I here are actually sitting on the sand in Cocoa Beach, and so the launch was at Kennedy Space Center. It launched there at night at 2 in the morning. It was a really nice sight. Here's a timeline. There's a little close-up picture of when the rocket actually ignited. Here's a timeline of its journey since launch, which was in August 2004, on toward its 6-year cruise until it gets to Mercury, which is just coming. So a year after launch, it flew by the Earth. It took some measurements. Next up, it flew by Venus twice, and then it flew by Mercury 3 times. We got a lot of the data, which is what I'm going to talk about. That was just an animation of its, well, let me play. Okay, so here's all the instruments that were included in the spacecraft, and I'm not going to talk about them all, but I'll just point out that this one on the top left is the one that was developed here at LASP, and the one that I worked on for my graduate work. It's the Mercury Atmospheric and Surface Composition Spectrometer, so MASCS. So as the name suggests, its objective is to measure the composition of the atmosphere and its distribution. And it also has the capability to look at reflected light from the surface, where we try to derive the mineralogy and composition of the surface. Here's some pictures of the development of the instrument here at LASP. These were taken actually in the clean room that you probably walked by when you first came in. So you can see kind of the size of the instrument. It's so big. Here's a close-up of the half of the instrument that I spent the most time on. This is the one that looks at the surface reflected spectra. this is a diagram of all the spacecraft activities that occurred during the first flyby. And I just put it up there to show you that it's a very complicated thing to sequence. There's a lot of activities and a lot of different instruments that wanted to take data. And by the way, the surface reflectance spectra only got data for about 14 minutes. So one of the first results is that we saw the half of the planet that we'd never seen before. So here's a map of the entire planet in this cylindrical projection. So here is the part of the planet that was imaged by Mariner 10. So less than half. All this side of the planet had been missing. So after the first flyby, we got our first glimpse of that part of the planet. During the second flyby, we filled in more of that area. And finally, for this last third flyby, filled in more of the gaps, and now we're seeing about 98% of the surface. If there's one geologic feature you should maybe remember from Mercury, it's the Caloris basin. It's one of the largest impact basins in the solar system. So in this image of Mercury, this is the side of Mercury we hadn't seen before. This area right there, that's the Caloris basin. Here it is close up. Mariner 10 only saw this easternmost sliver of the basin. So it's recognized as a very important thing. And they came up with a diameter shown by that yellow circle. It turns out that when we actually saw the thing, it was somewhat bigger than that. So I can see this is not going to come out so well, but one of the more powerful ways you can determine variations in composition of a planet is through color imaging. So there's an imager on the spacecraft, and you can take images in 11 different spectral filters, 11 different colors, throughout the visible and the near infrared. So there on the left is a mosaic of Mercury as we were departing, and that's in one color. You can make 3 color images based on that set. That's shown here on the right, and I think you can't see any colors there at all. But if you looked at it on my computer, you can see that the colors have actually been stretched somewhat. So that over here on the left, where you see these bright areas, these bright craters and crater rays, over here, they look blue. This area, the Caloris basin, is somewhat bright, and it actually looks red. And so the inference is that there are variations in composition reflected by these different colors. You can take that concept further. You can apply a statistical analysis on these 11 different colors that you obtain on the surface. And you can develop these 3 color images based on that are designed to accentuate color differences. And so I won't attempt to explain what went into that image, how exactly it was created, but it came from the color data, and it's showing you that there are real differences in the optical properties of the surface. So it doesn't tell you what the surface is made of necessarily, but it helps you identify, in a relative sense, what different color units are. So you can begin to explore that idea further. Before I go to the next step, I need to talk about a concept called space weathering. So on the moon, this is a process by which surface undergoes constant impacts by micrometeorites over geologic time. And that has implications for the texture and the state and the chemistry of the surface. And there are optical effects that come out of that. So here are two reflectance spectra of samples returned by Apollo. So here in the top is a spectrum of a material that has not been space weathered. You can see it has these depressions in it, and those are caused by the presence of iron in the silicate mineral. So these are very diagnostic absorption features that you what we'd like to see and tell you a lot about the mineralogy of the surface. This curve at the bottom, which has been weathered over time. By the way, both these samples are composed of essentially the same material. It's just the optical properties have changed due to this weathering process. So you can see there's a tiny little hint of that absorption feature due to iron, but it's been drastically reduced. So the upshot is that materials become darker over time, and their diagnostic absorption features get erased. When you look up at the moon, here's a picture of the moon from the Lunar Reconnaissance Orbiter up there right now. This is a relatively fresh crater on the moon. So it's bright and it has crater rays. Maybe in a few 100 million years, as this relatively fresh crater becomes weathered, it'll darken and fade into the background. So if you want to go look at the composition of the surface of the moon or Mercury, you really want to get spectra of small, relatively fresh craters. So as we flew along during the flybys, we didn't really have any active pointing. We didn't know what we were looking at, so we just pointed at the surface and took data. So here's the track of our instrument as it's going across the surface to one of these color-enhanced images. Can't quite tell from that picture, but it turns out we didn't actually hit any of the really interesting features that we saw in other parts of the planet. But we did cut across this tiny little, relatively fresh crater. So here's the spectrum of that crater in the top right. By the way, I put a little rainbow there. That's this is the visible part of the optical spectrum. So now, what we're looking for a little absorption feature like that at this wavelength, about 1,000 nanometers or micron. Somewhere around here, and it's not there. So you might say there's just this one crater, maybe, but camera on board, one of its spectral filters is actually near that wavelength. And when you look at the images in that wavelength, you see that other fresh craters don't seem to have that absorption feature. So the inference is that Mercury doesn't have iron-bearing silicate minerals like the moon does. That is somewhat puzzling. So here's a full global picture of Mercury on the right. Here's the moon on the left, both in the same wavelength, and hopefully at an accurate absolute scale, so you can directly compare the reflectance of the moon to Mercury. As far as I know, I haven't seen any pictures quite like that anywhere else. So what you see is that Mercury appears somewhat more uniform than the moon. The average brightness is somewhere intermediate between the darkest regions on the moon and the brightest regions on the moon. So it doesn't have these big expressions of iron-rich material that you see on the moon. By the way, these dark iron-rich areas, they're caused by impacts that have fractured the crust, and the iron-rich volcanic material underneath toward the mantle has risen up and flooded those basins. Now, there are actually more direct measures of the surface composition from the messenger spacecraft, from the neutron spectrometer, and this is a plot of their data during the first flyby. The details of the plot aren't too important right now, but this is the actual data, these black data points. These solid lines are estimates of how the instrument would have responded to different compositions of the surface. So there at the top, this blue line is what the estimate would be if it had been looking at a surface that's very low in iron and titanium. The red and green lines, what the instrument would have seen if it looked at a surface higher, much higher in iron and titanium. And you can see that the data is more consistent with that. So the significant result from that is, even though we don't see iron in the silicate minerals, there's iron in the surface. So that leads you to is that there must be iron in different minerals. They're not silicates. Yeah.
Could you say a little bit more about since the axis is time, it's confusing with which you're looking at this.
Yeah. So as the spacecraft is flying by, we have the field of view. The neutron spectrometer is pointed toward the planet. Very large field of view. So as we're getting closer and closer, it's getting better and better signal as we get the closest approach. And so all the time it's counting neutrons. So this is a count rate. So one of the limitations of this, of course, is that this is limited to the regions of the planet that we're seeing by this instrument. Other parts of the planet could be different. Now, earlier I said that there had been this debate in the community after the Mercury 10 results. Is it volcanism? Is it impact melt? So here for the first time there's actually clear indications of volcanic activity. So here's an image of one of the what's thought to be one of the more recent impact basins. And I thought I'd just go through some of the thought process about what this means. And of course the colors look terrible. But in this enhanced color image, this interior region of the basin has a different color than this outer annulus. If you actually go in and count the craters in that area, you see that the inner region actually has quite a bit less. The inference is that that region is quite a bit younger than this annular material. So it's younger, it's a different color, must be a different composition. There's also what's thought to be a volcanic vent over here, this bright area. So all those things lead you to this inner region was filled by volcanic material. There's more evidence for volcanism. And by the way, one of the arguments for the Mercury 10 images was that they were lower resolution. So they thought that perhaps resolution just wasn't good enough to see these relatively small structures. And so this is one of them. You can see the scale here. It's 50 kilometers. So relatively small feature. This little feature there is called an irregular shaped depression. And it's surrounded by this relatively bright material that's diffuse. And this is interpreted as a volcanic vent that's actually had an explosive eruption. And that's the material around it. There's more evidence for magmatic activity. Here is an impact crater called Picasso. It has these pits in the floor, and they're called pit floor craters. And what they think happened is that fracturing the surface, there's a magma chamber underneath, and as that magma withdraws, there's a collapse of the surface that subsides and creates these pits. And you see those on the moon. So the geologists would say that there's clear evidence for volcanism at work on Mercury now.
Current volcanism?
Not current. Clear evidence for volcanism. So the images alone don't give you a quantitative measure of the topography of the surface without more effort. So there's a laser altimeter included on the spacecraft. So as we're flying by during these flybys, there's a laser and it fires at the surface repeatedly. So as it fires a pulse, it starts a timer, the pulse goes, hits the surface, comes back, and the time it takes for that to happen tells you the distance to that surface. And you do that multiple times, you get an elevation profile. So here's the ground track of that altimeter as it cuts across the surface. And here's an image of the region in that sample. These yellow points are the measured height. And so what's interesting about this is that you see there's an impact crater right here. And over here, it's not so obvious, but there's a crater that's approximately the same size. But this one has been filled. So you can see that in this elevation profile. You can actually quantify that. You can see this crater is quite a bit lower, and this one's quite a bit higher. From that, you can derive how much material has infilled that crater and get an estimate for the volume of volcanism. I should have mentioned earlier those thrust faults. They only saw them on half the planet because that's all we saw after Mariner 10. So they wondered just how prevalent they were, and it turns out they're all across the surface of Mercury. So here's one of the newer ones that we saw. Based on the prevalence and shape and size of these faults, it's been estimated that the contraction was actually up to 30% greater than what had been previously estimated. And I'm sure that's a number that's going to be revised as we go into orbit. Here's an interesting geologic structure that's the origin of which is still being debated. This is something that had been called a spider, and now it's got a better name, Pantheon fossate. So you can see these are also faults here, spreading out radially. It's not clear if this impact crater is just placed there serendipitously, or if it actually had something to do with the creation of those features. Like I said, the origin of it is still being debated, but I think the basic premise is that this whole region was once smooth, and there was some activity underneath that actually uplifted the surface and created, instead of compressive forces, extensional force, and created these troughs. Here's another interesting feature that I don't think I've even read about any kind of explanation for yet. There's a crater, and this whole region is inside the Caloris basin. There are these bright crater floor deposits. This irregular shaped material on the floor of these craters that's extremely bright. And you can't explain it by a less space-weathered thing like that you can for, say, this little crater. So it's a really strange material that doesn't have any explanation as far as I know yet. The magnetic fields, of course, there's a magnetometer on board Messenger. During the flybys, we made measurements of the magnetic field. Now, like I said before, the magnetic field of Mercury is quite a bit weaker than that of the Earth. And as such, it interacts with the solar wind quite a bit more than what we have here. So the solar wind, which is always coming from the sun, is a plasma. It's composed of mostly electrons and protons. And it carries with it a magnetic field from the sun. It's a very dynamic thing that changes often, especially when the sun is more active. So that magnetic field interacts with the global planetary magnetic field of Mercury. It's a very dynamic environment. So here are some of the results from the first flybys. The intrinsic field dipolar. Yes, that's what was thought during Mariner 10. What that means is that you can explain and model the field by two poles, a north and a south pole, just like you can here. Has the field changed since Mariner 10? Not that they can tell. Are there any crustal fields? It turns out that Mars and even the Moon, there are these remnant or frozen, localized magnetic areas. And as far as they can tell, they didn't detect any. So on to the atmosphere, or the surface-bounded exosphere, which is, if you remember, is the other objective of the instrument developed here. I find the whole topic of the atmosphere, a little more difficult to think about. So there are three fundamental processes that will populate the atmosphere of Mercury. something called photon-stimulated absorption or thermal evaporation. You actually evaporate material from the surface. This is a fairly low energy process, so any atoms that are liberated from the surface don't make it up very high. And so some of those might actually go up off the surface and ballistically come back down and stick back on the surface. These two lower processes here, ion sputtering, so impacts from the solar winds, the electrons and protons can actually eject atoms from the surface, and you can actually have micrometeorites, which are always hitting the surface and spray the atoms up into the atmosphere. So if you get them up high enough, they can actually be pushed by the sun, solar radiation pressure, and it'll push them away from the planet. So all these are source processes, and over here these are loss processes. If the atom is up in here in orbit long enough, it can become ionized. And once it loses an electron, it becomes ionized, it can interact with the magnetic field of the planet and the interplanetary magnetic field. It can either get carried away or it can get pushed back down to the surface. So here are some of the results from the measurements of the atmosphere during the flybys. Here at the top are measurements of sodium. So this is sodium this is neutral sodium that's illuminated by the sun. And these are invisible wavelengths, and this is actually the same wavelength that you see in sodium lamps used in parking lot. So you can see this distribution. There are peaks in the north and the south. Here at the bottom is calcium. You can see the distribution is quite a bit different. Calcium seems to peak toward the equator. And the point here is that there are apparently different source processes for different atmospheric constituents. And they lead to different distributions. These distributions change over time as well. So there are seasonal effects. This is the distribution of sodium during the second flyby. Here's the distribution during the third flyby. It turns out that the distribution is actually the same, but it's quite a bit weaker by something like a factor of 20. And these kinds of effects are expected from the models, but this is one of the goals of the instrument, is to measure these kinds of effects in more detail. Right, so quick summary here. So apparently there's no silicate minerals on the surface that contain iron. And this is very much unlike the moon. But there are relatively high amounts of iron and titanium detected from that neutron spectrometer and from other arguments based on the absolute reflectance of the surface. So there must be iron in a mineral different than silicates. And there are minerals like that on the moon. There are iron and titanium oxides, but they're most often associated with silicates that also carry iron. So why you have iron-free silicates paired with iron-rich oxides is still something of a mystery. We have clear evidence of volcanism at work on the surface that has shaped the geologic history. There are subtle variations in the optical properties that we can infer that the surface has a heterogeneous composition, varied. The thrust fault seen from Mariner 10 appeared to be ubiquitous in contraction of the entire planet. Seems to be more than what had been estimated. The magnetic field measurements are consistent with a molten core, and the atmospheric measurements, as we just saw, show a lot of variability and indicate different source and loss processes at work. So the main part of the mission is actually just starting in March when we go into orbit. So we'll go there for a 1-year nominal mission, mapping, high resolution, and all the colors during that year. There's actually the next mission being planned currently. It's called effe Colombo. It's planned by the European Space Agency. It's due to launch in 2014 and arrive in 2020. And actually, a lot of our European colleagues are here at LASP this very week, working on the data, the magnetic field measurements, and the charged particle environment around Mercury this week, and actually in this room. So it'll go for a 1-year nominal mission. It's a little different than MESSENGER in that it will actually be composed of 2 different orbiters, one study the magnetosphere in detail, and the other one dedicated to the surface. So, yeah. So one of the aspects of Mercury that I find interesting is that the apparently disparate fields in the atmosphere, the magnetic field, the surface, and the interior, they seem quite separate, unrelated. And a lot of people might say they are, and they study only the magnetic field or only the interior. But on Mercury, it seems that they're interconnected in significant ways. So what I've attempted here is just to draw lines of influence. So here the interior influences the magnetic field. It's the source of the magnetic field, the molten, conducting liquid core. The interior also, of course, influences the surface through volcanic material. Also, those thrust faults are caused by the interior cooling over time. The surface is ultimately the source of the atmosphere. So when you see sodium or calcium or potassium, those atoms come from the surface. The magnetic field influences the atmosphere because as those atoms become ionized, the magnetic field can either carry them away or precipitate them back to the surface. And the magnetic field can either protect the surface from the solar wind as it comes in, or can actually direct solar wind particles to the surface, just like we have aurora on the Earth, where there's electrons, protons come in on the magnetic field lines and they precipitate in the polar regions of the Earth, and we see them because they interact with the atmosphere, but there's no atmosphere here. So all those particles end up hitting the surface directly. Okay, and that's all I've got.